Yeah, so I hope everyone had a good break, maybe had a coffee to refresh. After we've seen quite a bit of content on Dawn, and we've talked quite a bit about Dusk as well. We in this session we want to really learn what Dusk is, and kind of give you a good overview so that you understand how Dusk fits in climate and weather models. So that's the introduction to Dusk, a minimal and lightweight front end for Dawn, and we will see what this exactly means. So first, I want to answer the question of what is Dusk actually. So we know it's a front end, but I kind of would argue that Dusk is three kind of different things. Firstly, Dusk is a programming language. Well, it's technically not Turing complete, but I think we can still make a case that it's kind of a language, or at least it's a stencil language. So you could say Dusk. Well, there's a language called Dusk Script, or I think more appropriately, there's a Dusk stencil language. And this language is a domain-specific language targeting climate and weather models, and it is embedded in Python. So it's an eDSL and an embedded domain-specific language that is embedded in Python. So that's kind of the Dusk language. But Dusk is also a compiler or transpiler, if you want to call it that. So there's a command line interface. You can, with this command line interface, you can do what you would expect from a normal compiler, similar to, let's say, GCC or a Fortran compiler. And this command line interface, it can compile this kind of Dusk language, this embedded DSL to SIR, and then Dawn can convert this further. Dusk can also call directly into Dawn to generate C++ directly, and then we will see what this means in a few slides. And then thirdly, Dusk is a software component that's the functionality. The main functionality of the software component is to translate this Dusk language to SIR, or then indirectly C++. And the software component also contains a Python API to programmatically get access to this translation functionality. And we'll see what this means. Dusk is written in Python and currently has no dependencies other than Python standard library. And we will see more about this as well. So we kind of, to start off, I want to give you an introduction to kind of this these 2 points, what this really means, because that should kind of clarify how Dusk fits in a climate and in a weather model. And then at the end, we will look at the actual language. I think that'll be quite interesting. So you've all seen kind of this hierarchical, this visualization of the Dusk's and Dawn's architecture. So kind of we started with a Python file, then Dusk can translate this to SIR, and then we've seen quite a bit about Dawn. Dawn will produce, for example, C++, or it could produce something else such as Fortran. And we've seen quite a bit about this, and now we kind of want to look a bit what's inside of this Dusk and into this Dusk's framework and software component. So like I said, there's this command line interface, and this command line interface, it takes a Python file, and then it will use the translation functionality to produce this SIR. But next to this command line interface, there is also a Python API. And this Python API, actually, instead of taking a Python file, it can take a Python, well, what would be something like a function pointer. So in Python, basically everything is an object, and when you define a function, then this will be an object as well, and you can take this function object basically, or what would be maybe more familiar as a function pointer, and you can pass this to the Python API. And then you get access to the translation functionality for Dusk through this Python API. And then in Dusk, there's also this kind of small compile module, which is kind of mostly a wrapper. And this wrapper, it can call into Dawn's compile functionality, and it can call it, and then it can pass this generated SIR directly to this compile function, and then you can directly get C++. So kind of this is, let's say, a shortcut if you're not too interested in invoking Dawn yourself, you can just use this directly, and then you can use, for example, the command line interface or the API to directly go from Python to C++. Or if you really want to, you can say, well, I only want the SIR, and then with the SIR, I will take care of invoking Dawn itself, and I can pass all the options and have more control over how Dawn gets called. And maybe a few words on this Python API. I feel like I think this is also kind of a nice thing. I mean, we will use this Python API in the notebooks. So the notebooks are Python based, and then this Python API comes quite handy because then our Dusk stencils are fairly well integrated into these Python notebooks. Also, we use it internally for testing, and there's two other use cases where this can come in useful. One is, for example, if your build system is based on Python, then instead of in Python using the CLI, the command line interface, to then kind of invoke other Python code, you can directly use the Python API and have a more integrated approach here. And then lastly, I think if you like this Python API is useful if you, for example, want to have a let's say a more Python integrated way of writing your models. So for example, if you want to write other parts of your models in Python as well, then you can naturally use this Python API to get this translation functionality of Dusk. But this is kind of the Dusk framework, right? It has the main functionality is to go from Python to SIR, and it has this different API entry points. And it also, if you don't want to like invoke Dawn yourself, you can kind of do this with this shortcut way through Dusk itself. So yeah, that to kind of give you an idea how Dusk fits into, for example, into a model and how an integration could look like. Now we want to focus on the programming language. So that's kind of what we've been working We've been working up to this so far. And I think this is where things get really interesting, because that's kind of also where a lot of the meat is going to happen, right? I mean, we want to write a model at some point, and we want to know how we can do that. And I think that is something that affects domain scientists a lot, and I think we should be interested in that. So to have a look at how this works, we want to look at where the stencils are, because Dusk is focused on these stencils, and we want to see where these stencils are. And basically in a weather or climate model in such a code base, there is a lot of code, and this code will take care of a lot of things other than stencils, right? So there's code that takes care of initialization, it sets up the MPI ranks, it sets up the mesh, there's a whole lot of initialization that has to be done. Fields have to be initialized. Then there's a whole lot of file input output happening. Data files are read, config files are read as well. Components are configured, and probably we want to do some logging. And then there's a whole lot of other things that affect file input output. Then there's the actual simulation and the calculations happening. And there we usually distinguish between the dynamics part and then the physics part. And then there's some other components, and then such a code base is very big, and there's many components. And basically the stencils, most stencils are kind of live in these two components. And at ESiWACE, we're mostly kind of interested into this dynamics component. The physics component we kind of port with OpenACC, and the dynamics component is what we are interested in when we want to DSLify basically such a model. But I also want to point out that the physics is currently not something we look into too much with the DSL. However, this may change in the future, and I think there could be also some interesting things we can do here with DSLs. But for now, we're kind of focused on the dynamics. And these two components, they are a major part of the runtime. And the idea is to use a hardware accelerator to speed these up. And in our case, for example, we could use a GPU to speed up, let's say, the dynamics part. So I want to kind of show you how this kind of works. So we want the stencils to run on the hardware accelerator, right? So in our case, that would be a GPU. And there's still code running on the CPU, right? We can't run just the whole model on the GPU just like that. That would of course be nice, but GPUs are not that suitable to just run the whole code base on them. So this code, this code running on the CPU, it still decides, that's kind of the code that decides when and how these stencils are run. So for example, we could think of a timeline that starts from the top and goes to the bottom. And then this part on the CPU, it will say, well, first we call this stencil 1, and then I reach get back control, and then that's called stencil 2, and so on and so forth until we called all of our stencils. And maybe this, let's say, linear way of thinking is not that accurate either, because we can have asynchronicity and parallelism there. But kind of basically it's the dynamics part that kind of decides when and how these stencils are being called, also what fields are being passed in there, and then at what point, and the order, and so on and so forth. So this CPU part, it's kind of it drives these stencils, and basically that's what we call the driver in a way. So maybe also the disclaimer. So the stencils are, if we go back here, so the stencils are part of the dynamics, right? But we want them to run on the GPU, but there's still code that is the dynamics, but that are not stencils, and this code decides when and how these stencils are run. So in this illustration, we want to kind of distinguish between the dynamics part that runs on the CPU and the stencils that would run on a GPU, even though the stencils are part of the dynamics, and not all dynamics will run on the CPU, such as especially the stencils we want to run on the GPU. And basically the dynamic part that runs on the CPU, we can kind of intuitively give it kind of designated as the driver code, because it drives when and how these stencils are run. And with this word driver, this is kind of unrelated to hardware drivers per se, but I mean, that's kind of the idea of hardware drivers as well. They drive the hardware, they decide how and when this hardware kind of is utilized. So in concept, the word has an analogous meaning. So this CPU part, this is what we call the driver. It drives the stencils that run on the GPU. Another question is, well, where does Dusk fit into this? Where is it? And basically, Dusk is mostly the stencils. So I think a good way to think of Dusk is that it is a stencil language, and the idea is that all of Dusk will run on the GPU. However, this line, this line in this distinction, it's not always that clear, and I want to show you two examples where this line kind of falls apart. So as a first example, let's say we have a bigger stencil that runs on the GPU, and then there is two parts. There's a first part and there's a second part of the stencil, and in between we kind of want to do a global synchronization between fields, so that the second part has updated fields, and to ensure that we don't have race conditions between these two parts, and maybe we really need this global synchronization between these two parts. And the way you do this with CUDA kernels is that you run one kernel, you synchronize back onto the host, and then you run the second kernel on the device, and that kind of allows you to do a global synchronization this way. And what we can see here is that, well, now kind of there's part of the control flow that went onto the CPU now, right? So we have to make sure that after we call the first part, we call the second part, so that we don't change the semantics of the stencil, basically. And to take care of this, this has to run on the CPU, and it kind of it basically is part of the stencil, but because we had to break the kernel, we needed to run some control flow on the CPU, and this part kind of still drives the stencil, right? So what was before stencil code now all of a sudden runs on the CPU, and it drives these stencils. And that's kind of, yeah, so that's kind of a bit misleading, right? This distinction here, it kind of falls apart because even though it is on the driver side, and you can consider it a driver, it's really was originally part of the Stencil, and we don't really consider this driver code. And another example is that we have these three stencils again. And then there's some code between two stencil that runs on the CPU, and that was originally driver code. And to get better performance, we want to merge these two stencils together because we don't really need this sync, or this synchronization can be fairly expensive, and we want to avoid this synchronization. However, we still have this kind of bit in between that maybe was really important, or like it did something crucial for the second stencil. So we want to combine these two stencils, and so we just combine them. But the question is now, well, okay, but this code, we needed this, and so what we do is we just let it run on the GPU too, and then it kind of disappears on the CPU side, and now it runs on the GPU. And what was kind of previously driver code on this side has now become part of the CUDA kernel, and it kind of runs between these two stencils on the GPU. So here kind of this, well, you could still call this kind of, well, it was previously driver code, right? But now all of a sudden it's stencil code. So this kind of, the point is this line between driver code and stencil code it's a bit blurry, and sometimes things can kind of change in between depending on what you do. Nevertheless, I think this distinction between driver code and stencil code is still very reasonable because it allows us to think about, well, what are the stencils, and then what is Dusk, because Dusk kind of focuses on the stencils. And I think it is, well, it's more of an intuitive concept, but I think it's still reasonable for this illustration, even though the line is a bit blurry. So Dusk is, like I said, it's mostly the stencils. Dusk, it requires driver code, and the driver code decides how and when the stencils are run. The driver code will set up the mesh, and it allocates the memory. The boundary is sometimes a bit blurry, and it can change. And also simple driver code can run on the CPU, and it can also be written in Dusk. And it's likely that this will kind of grow further, that we can maybe run more more driver code onto the GPU, and what this allows us to is kind of merge bigger stencils, and then when we have bigger stencils, when we merge them into bigger stencils, we kind of have a bigger picture of the whole computation, and this allows us to do, this gives us more optimization opportunities. So in the future, it's likely that we kind of, this will extend a little bit, but also I think there's some, well, there's some limitations, and then in some cases it probably doesn't make sense to just run all the driver code on the GPU. So about the Dusk language, so Dusk is a subset of Python. So this is kind of on the syntactic level. So if you or let's say on the textual level, Dusk is fully statically typed. Now you might say, well, this is weird because Python has dynamic types. But in fact, Python added optional type-ins in version 3.5. So that was in 2015. That's 5 years ago. And they are optional, right? However, in Dusk, when Dusk translates this Python code, it will check and it will enforce static types. So if your type-ins are missing, or if you have dynamic types, then Dusk will reject this code, and Dusk will make these type-ins mandatory and will enforce them. And thus Dusk is really statically typed, even though Python is not. And then Dusk does assign different meanings to Python language elements. So there are differences on the semantic level, and we will kind of see a bit what this means as we continue. So a word on this as well. So Python can do many things. For example, we can start a web server in Python, but we don't really want to start web servers in stencils, and we don't want to run web servers on GPUs. And because of this, a lot of Python language elements are disallowed in Dusk. So we actually, Dusk, you cannot start web servers and GPUs, and I think that's probably a good thing. And hopefully we will not need such stencils in climate and weather models. Also, yeah, we do assign different meanings to some Python elements. And the reason is to kind of make the Dusk feeling more ergonomic, so to give it a bit of a better feeling, especially when writing climate and weather models. And Dusk does target domain scientists, possibly with a Fortran background, and it may upset some experienced Python developers because we do reassign meanings to Python elements, right? So if you know what this Python element means very exactly, it's likely that you will be thrown off because it can have a different meaning inside of Dusk, because we found that it's because this is more useful to give them an ergonomic feeling for domain scientists. And this was actually a very deliberate compromise, right? We are domain scientists are much more our target audience than let's say a general Python developer. And full disclosure, I was actually one of those upset Python developers. When we made this decision, I felt like this was wrong, because we sometimes assign different meanings to Python elements, right? And after a few weeks and months, I feel like this was the right decision, and I feel like this decision makes writing stencil codes kind of more natural and gives it a better feeling. So yeah, this was a deliberate compromise, and then I think this was the right choice in this case. Okay, so let's look at some actual code. So here we have some Python code or Dusk code. The red highlighting here, this is Python keywords. And then the blue highlighting, these are kind of keywords introduced by Dusk. So they're not really Python keywords, but in Dusk, they are kind of keywords that we added or that we gave special meaning in this Python example. And we will kind of quickly go through this example together. So yeah, at the top, we do this import to kind of import these magic keywords. Technically, we don't have to do this. We can, even without this import, we can fully parse and translate this whole stencil. But the reason why we still prefer to put in this import is because in this script module, we define what these blue elements kind of mean in a Python world. And this is very useful because Python world has very good tooling. There is very strong IDEs that give good auto completion, and they can warn you about potential errors. And because we give these kind of Dusk keywords, we give them meaning within kind of Python. The idea is that these good Python tools, they will not be confused with these kind of new keywords by Dusk. So with this import, kind of you can use your linters, you can use your auto completion, you can use very powerful Python developer tools, and they should reasonably they should allow you to reasonably use these tools and make use of this these very powerful tools in the Python development environment. So with this we can import these things. Of course, it's not always possible, but I think we so far we're on a good path where we have been able to kind of express our keywords in Python basically. So then we have this is the @ symbol here, might not be that easily recognizable in this coding font, but this is an @ symbol, and this is called the Python decorator syntax. So you can decorate functions with this syntax, and this is in fact this here is a function definition, and this is decorated with this stencil decorator. And this stencil decorator, it marks a Python function. So this Python function is marked as a Dusk stencil. And that's the code that Dusk will look at. The command line tool or the translation functionality will focus on these Python parts, and that's what it will translate. And other Python code will be ignored. So you can also have other Python code in here, and Dusk will ignore this other code, and you can intermix it. But yeah, that's how the marking works for Python functions. And then the name of the Python function will be the name of the stencil. So our stencils are named in this case. Next, we have some field definitions. Field definitions are Python function parameters, and we will see a lot more on these later on. So then we have here a Dusk kind of language element. So in Python, this has kind of, let's say, a different meaning than it has kind of in Dusk, but we feel like this is, here this is where we made one of those compromises, and I mean, I personally feel like this was a good choice, and this kind of is a nice way to express this. So basically, what this statement means, it means apply the stencil on the whole domain, and we will learn a lot more about what this means later on. And then, well, the body, this is what we compute. So this is a very simple stencil. It's a pointwise stencil on two fields, A and B, and extents and neighborhoods, they will also come later. So for this introduction, there's quite a few forward references, but especially tomorrow, we will really learn a lot what, and also in depth what all of these elements mean. Also, I want to kind of give a quick introduction on temporaries because they also relate a bit to driver code, and also a little bit to integration. So I think it makes sense to do this at this point. So sometimes we want to store an intermediate result temporarily, and to make the code more readable. And for this, we have something called a temporary field. So we can introduce a temporary field. It has the same type declarations, and we have to declare this at the lowest indentation level and usually at the top of the stencil. So we put this here above this iteration domain statement, basically. And once we have introduced this, we can, for example, compute a value and then store it temporarily into this temporary field, and then we can reuse this. And this allows us to hopefully write more readable code instead of having to kind of, I mean, this is a very simple mechanism. But there's kind of, there's some importance to this, and we want to highlight this real quick. So we distinguish between what we call API fields. So these kind of parameters of the stencil, we consider this kind of part of the, let's say, the API of this particular stencil. They're part of the signature of the stencil, and we distinguish between these temporary fields. So they, and basically the API fields, they are allocated and deallocated by the driver code. So this might, maybe this could also relate to this OpenACC question that we had before. And in our case, we kind of assume that, or we expect the fields to already exist on the GPU. We don't really so far have much infrastructure to see whether a field already exists on the GPU and whether we need to transform it. Right now, we kind of expect that, well, the field is already on GPU, and it's unclear whether we want to add such an infrastructure later on. But I mean, in Icon, I think most of the DICOR has been translated with OpenACC, so this assumption kind of works out fairly well. Then they persist between stencil runs because they're initialized and allocated by the driver. So once the stencil, when it starts, they are already there. When it stops, they will still be there. And basically, what this means is these fields are owned by the driver code. So we kind of only, well, we use them while we run the stencil, but we don't really own these fields. And then those temporary fields, they are allocated and deallocated by the generated stencil. Then they only exist while the stencil is running. So this is kind of from a conceptual point of view, they only exist while the stencil is running. Maybe for optimization purposes, we could reuse existing temporary buffers. So then this statement might not be 100% true on the implementation detail level, but from a conceptual point of view, this the lifetime of this temporary field is within the start and end of the stencil, basically. And so as such, they are owned by the stencil. So the driver code kind of has no business about these temporary fields, and then they only exist within the stencil, and the stencil owns them and then decides what happens to that. And Dawn is free to remove or add temporary fields during optimization passes. So as an example, here we see, well, we do compute a value and store it into this temporary field. However, for the rest of the stencil, we don't really use this, so this is kind of a dead assignment. So we can remove this assignment without really breaking anything. And once we remove this assignment, we see that, well, the temporary field is not used anywhere. And then we can also remove the temporary field. And Dawn is free to do that. And in some optimization passes, Dawn can introduce temporaries. And I think at least in the on Friday in the performance session, you will see some cases where this might occur. However, Dawn must respect and preserve how API fields are mutated. So, for example, if we remove this assignment here, then you could argue, well, A is not used anymore in the stencil, but Dawn really must not remove this assignment because this A, it is an API field that is used afterwards, and we cannot just change the stencil so that it produces kind of a different A. Dawn really must respect these API fields. So that's, I think, an important distinction. So after having said so much, I also need to say you cannot use them in the exercises. Please don't use them. There's a small bug in the naive CUDA, in the naive CPU backend, and you will do the exercises with this backend, and then because of this bug, you cannot use them. So don't use them because you will get C++ errors. That's of course a bit unfortunate to have talked so much about this and then not allow you to use this. But that's all the exercises should be very much solvable without temporaries actually. All right, and here next we want to do a comparison between Dusk and Fortran. So on the left-hand side, we have Dusk code. On the right-hand side, we have Fortran code. And always these codes kind of correspond to each other. They're kind of a, let's say, very straightforward translation from each other. And we kind of want to go through some examples and look at some differences. Also, these codes, they're kind of, well, some fields or many fields have been renamed. And some operations have been changed. So these codes don't really correspond one-to-one to real code anymore, but they are still kind of heavily inspired by real-world code as seen in Fortran-based weather models. But the idea is really to kind of compare the look and feel between these two languages and kind of see what are differences and how it kind of works out. So having said that, we will look at first one difference. So for example, here we have a field E that is being used in Dusk, and in Fortran it's used as well. And what we find is that there's a lot of contextual information, which are basically these indices here. They have to be explicitly specified in Fortran, and in Dusk we don't have to do this. And Dusk kind of fills this in by default. And basically it fills it in with, sane defaults, but basically it kind of deterministically fills those in. So there's no like kind of black box artificial intelligence, dark magic involved. It's very deterministic how this is being filled in, and it's very easy to develop an intuition to be able to expect what Dusk will fill in there. And if you want to fill this, or like if you want to use different indices, then there's very straightforward ways to do this in Dusk. And because of this, kind of the code is less verbose, because most of the time, the majority of the time, we don't have to fill in these indices, and the code is kind of more to the point, because we basically just write E when we want to use this field. Here's a kind of a stronger example of this case. So here we just use C. And here in this Fortran code, there are some neighbor tables involved, and they require their own indices. And then there can be quite a bit of indices to be filled in. And this can become pretty big, and we can automatically fill this in. And automatic kind of means deterministic. So you it can very easily develop an intuition of what to expect there, and it's kind of very straightforward. There's not like a black box approach here. So you might say, So then Dusk does provide, generally it does try to avoid code clones. So in this case, we have here this B minus C that we compute, and we have this twice up here, and then on the next line it's in there again, and we can avoid this in Dusk. However, you might say, well, those aren't code clones because they use, well, different indices, right? They're kind of the same expression, but we use different indices both times. However, that's true, but because we describe this algorithm or this stencil on a higher level, Dusk will be able to fill this in automatically as well. And then what the sum over means, we will learn about this tomorrow, quite in depth. And next we also use these high-level constructs to describe local neighborhoods. Whereas in Fortran you kind of use this lookup, this neighbor lookup tables, and in this case, kind of you don't really know what this neighbor table is until you looked up how it's initialized or what the neighbor table contains. Whereas in our case, the neighbor table, well, it's not used directly, but we kind of describe which neighborhood we mean, and then the appropriate neighbor table is automatically used in this case. Also more on this actual syntax later. We will learn about this tomorrow. Nevertheless, I think we can appreciate similarities. So both Fortran and Dusk, they support this written out or logical operator. Not all popular programming languages have this. Both Fortran and Dusk, they both have it. Well, Python has it, and then naturally Dusk has it as well. And next is kind of power operator. This actually also Python has this, and I think there's even less popular programming languages that have this similarity. So we kind of automatically benefit from some of Python's similarity to Fortran. Also, a word of caution for the exercises. If you want to use this right now, there's a small issue where if you use an integer type, then you will get a spurious type error. And basically to fix that, you need to just use a float type for both components, and then you can fix this issue. But this is really a small kind of spurious typing error that we can fix. So here's another example. So this one kind of is a bit stronger as in the aspect of we have here quite a few lines of code, and in Dusk we just have one. Now I think lines of code is not necessarily that good of a measure to say whether something is readable or not. This lines of code is, I think, on its own a very poor measure. But still, I think here we have kind of an extreme example that we also want to go through. So this is a bigger neighborhood. It contains this contains 4 neighbor locations, and you can see how basically in Fortran we have to, for each kind of those 4 neighbors, we have to repeat this expression and then kind of adjust this index here. Apart from this, it's like these are kind of all co-clones. And because we describe this on a higher level, Dusk can automatically unroll this expression correctly into this basically this expression and fill in all these indices for us. And what's nice about this example is that we concisely describe what we compute, which is O multiplied by P, and also where we compute this. And in this kind of purely Fortran example, this information exists in there as well, of course, but it's kind of harder to kind of read this out. And we have nicely separated this in this on the Dusk side. And then, yeah, they're separated and they're not interleaved. And I think that's something we can appreciate. Yes, this is a bit of an extremer example. And I think not every example will see such a big change, especially when it comes to the line of codes. But I think this benefit is very real, and I think something like this can happen fairly regularly. So I would argue that there's very real benefit. So this benefit that we see here, not all of it will see it, but I think we will see it very regularly, and there's a very, very real benefit from expressing this kind of in this Dusk way. Here's another example. So this is a more moderate example. In fact, we can see that Dusk actually this time has more lines of code than Fortran. So yeah, I think, I don't know, lines of code on its own, I think is a very poor measure of code quality. And actually, Dusk actually has some redundancy here. So for example, this expression D is expressed twice, and it's only expressed once in Fortran, and the same can be said about this E expression. So Dusk doesn't kind of make your code, it doesn't magically remove all of the redundancies. And it doesn't also make your code very high quality magically on its own. And I think it's honest to acknowledge this for an honest and fair discussion. And maybe to elaborate on this, so this introduces an element-wise multiplication with a weights vector. And for some stencils, this is necessary, and you will also learn probably tomorrow what exactly this means. Nevertheless, overall, Dusk kind of the example here is expressed in a more high-level way. And maybe also a word on this. So Dusk kind of naturally has an edge over Fortran because they target different domains, right? Dusk is specific, it's domain-specific language, and it's specific to climate and weather models. Whereas Fortran targets a much more general domain, which is numeric computation and scientific computing. And as such, in Dusk, we can afford to introduce elements specialized for climate and weather models. And then that kind of makes it obvious why Dusk naturally has an edge over Fortran in the domain of climate and weather models. So now some general information about Dusk. So Dusk, a minimal and lightweight front end for Dawn. Well, minimal and lightweight, it kind of has been growing steadily. So maybe this will leave your definition of minimal and lightweight at some point. It was started in May 2020, so it is fairly young. Right now, it's sitting at 2.6 thousand lines of code. That's pure Python code. It has no dependencies at all. It only depends on Python standard library. However, in the future, we might add small dependencies. There's some really nice kind of smaller Python libraries, and they've in some cases become de facto standards in the Python ecosystem, and we might make use of them in the future. But currently, we only rely on the standard library. It currently only works with Python version 3.8. There's no specific reason why we only need this Python version. This can be changed in the future, although it's not it's not an extremely simple change, but I think it's not an extremely humongous change either. So it's kind of, this would take, let's say, medium effort. But right now, Python 3.8 works for us. And most functionality is a rather light translation pass from Python ASC to SIR. So kind of Dusk doesn't do a huge amount of analysis or transformations, or like it's not a very, let's say, there's not a lot of smartness in Dusk when it comes to how it changes the code. It's kind of very straightforward, and I think stupid code can sometimes be really, really good because very often it will meet your expectations, whereas very smart code can be very dangerous because it might be very hard to know what to expect of such code. And so it works very close to SIR for unstructured meshes, and I think that's that's within the goal of a minimal and lightweightness, and I think it's always nice to have simple components. And that concludes our presentation on Dusk. I think I went a little bit over time, but we still should have plenty of time for questions, and I hope I was able to kind of give you kind of a bigger understanding of Dusk and how it could fit in a weather model on the one hand, and on the other hand, I hope I could give you a kind of a first look at the Dusk language itself. So after the question session and the break, we will have exercises, and then you can get your hands dirty there. And so we have some time for questions, and also I would like to encourage everyone to you don't have to be shy about these questions. We're very, very happy to answer questions, and we hope to have some interesting discussions. So please don't hesitate to really throw your questions out, and then if you want to, you can also add some comments. So thanks a lot for your time, attention.
Thank you very much, Ben. It was a very interesting presentation. We will now read the questions from the Google Doc as before. So we already have two. So the first question from Will. So let's say I've written the full model, let's say a die-core with tracer advection in Python, and I've written the die-core advection kernels in a Dusk-friendly way. Can these kernels be run through the Dusk to Dawn toolchain, and thus there will be a seamless integration of the original Python model with kernels running, say, on accelerators? Or are there a lot of steps you have not mentioned which makes the integration less seamless?
So the question is, well, are there steps missing, right? I think that's a good question. I think I would say no. I think we've tried to kind of we try to cover kind of also a bit how this integration could look like, right? Also in your presentation, Giacomo, before the break, you went into this, and I think with all of this, I would say I don't think you should expect really any additional steps. I mean, you will probably see unexpected issues. Maybe you will see some nonce and then something went wrong and things like that, right? But I don't think there's like a systematic step that's missing, like something that you need to do based on what we've presented so far. And then I think it was also a bit the goal to kind of up to this point to give you an idea of what it could look like to integrate all of these frameworks or these components into, or how to make use of them in a climate and weather model. So I think there should be no additional systematic steps apart from, let's say, unexpected issue because maybe something small went wrong. But maybe Giacomo, you can also add a comment to this.
Yeah, maybe I can add, if I understood correctly, you mentioned that, Will mentioned that, well, you could write parts of the model also in Python. So I think you want to write basically everything in Python. In this case, I would say no. At the moment, you still need some, let's say, C++ driver code. Unless you find a way to prepare, let's say, the input fields for the stencil calls from Python, which I think maybe you could do. But yes, at some point you need to launch some C++. Um, but yeah, maybe we can think about it and write it during the break. We can reason about this.
Yeah,
If I can chime in also in the discussion, can I?
Yeah, sure. Sorry.
Yes, just to complement, because I think what Giacomo was saying, right? C++ and Python, they interoperate nicely. So from Python, actually, you can make a call to the generated code and then integrate it in a driver code of Python. I think probably what would be missing, it depends on the data model. I think the data model is what you really need to connect the data model of whatever you're using in Python as a driver code to the data model that is assumed in the generated code. And right now we are working in the integration with Fortran with the compatible data model. But if one would think of a different layout of the data fields and so on in a Python driver, then one will need to work on some interfaces in between. But that's the only thing I think need to require additional steps.
Okay, perfect. So I guess let's move on to the next question from Raymond. How much exchange with model developers goes into the development of a DSL? Is there a test on how model developer friendly the DSL is? That is a good question. Ben?
I think today and the next few days is a very, very important test. So full disclosure, unfortunately we've not had a huge amount of exchange with model developers when it comes to this. We are honestly always very open and very eager to get feedback and get opinions from model developers. I mean, up to basically so far, a lot of our kind of infrastructure hasn't really been, let's say ready. So I think there's also let's say a limit because of the prototyping nature that I mean, basically we could have shown model developers such code, right? But I mean, running this code has not really been possible before May, and then after May, it took also some time to kind of get the features up so that you can run, let's say, you can write reasonable code, right? So we're kind of, it has not been a long time, and then we're still not really fully there yet where we can say, well, you can write many different, let's say model codes, right? So unfortunately, there has not been that huge of an exchange, but I kind of want to stress that we're always really eager to get feedback, and then I think today and the next few days for us it's very we've been really looking forward to this, and we really hope to gain a lot of feedback. And I also would like to encourage you, like if you have opinions on for example, such keywords, or if you have if you notice something while you write this code, or if you see things that throw you off, then we're really eager to hear that, and hopefully in the future we can get let's say a really good balance to make sure that this also makes sense for model developers. I mean, after all, this is a huge target audience of ours, and really want to focus on this.
Okay, I will read also the next question by Daniel. If the driver code needs to be written in C++, does that mean that I can't incrementally port the original Fortran code by successfully rewriting individual kernels in Python Dusk and call those instead of the original Fortran code? Answer this, Ben, or
if you want, you can take it. I don't mind.
I thought also that it's more related to the integration. Now I think you can incrementally port. I think, yeah, the example of C++. Yeah, maybe we should have said whatever language your model is written on, and let's say, so as I shown you can export a C header or a Fortran 90 interface. So yeah, you can also do the same from Fortran and iterate your substitutions. Yep, I think.
And in fact, I could also add this, like as you showed during the integration slides, this is actually what Daniel is describing here is probably the main strategy that we are following for icon, right? So it's not that you can do it, it's probably what we're actually following, yeah.
Okay, thank you for all the questions. So if there are no more questions, I think we have planned a break now, 10 minutes. So I would say let's reconvene at 4:35.